So to start off our unit on acid-base chemistry, we wanted to talk about two of the most common theories of identifying what makes something an acid and what makes something a base. And so that's the Arrhenius acid-base theory and the Bronsted-Lowry acid-base theory. The Arrhenius acid-base theory is kind of the foundation, and that is an acid is anything that produces hydrogen ions in solution, not hydrogen gas, but the hydrogen ion. And a base is anything that produces a hydroxide ion in solution. So off to the right, these two examples, we have something like HCl that's breaking down to form H plus and Cl minus, and that formation of the hydrogen ion is what makes this reactant an acid. And here we've got NaOH breaking down to form sodium ions and hydroxide ions. And that formation of hydroxide ions is what makes NaOH, or sodium hydroxide, a common base. Okay? A lot of what we're going to be looking at throughout this entire unit in acid-base chemistry is the reaction between hydrogen and hydroxide, which is going to be the formation of two hydrogens and one oxygen, or water. A lot of this chemistry takes place in water, so it's that interaction of how things play out against water. Right? The second formula, the second theory for acids and bases is the Bronsted-Lowry acid-base theory, and that is all focusing on how the hydrogen plays out within a reaction. So Bronsted-Lowry's acid-base theory says that an acid is anything that donates a hydrogen ion, and a base is anything that accepts a hydrogen ion. So we're just focusing on what is producing or giving up a hydrogen ion and what is receiving a hydrogen ion. So if we're asked to diagram a reaction involving ammonia, and this is our formula for ammonia, all right, because H2O is water, we're also told that this is a commonly known base. So one of the things that we're going to do is write a capital B under the thing that we can identify as a base. And then by default, because this is an acid-base chemistry, bases react with acids and acids react with bases. In this example, water is going to act as our acid. Okay? So if this is looking at the Bronsted-Lowry acid-base theory, acids are things that donate hydrogen, bases are things that accept hydrogen. So this water is going to give up one of its hydrogen ions, it's got two of them, and give that to NH3. So one of the things that's going to happen is one of those hydrogen ions is now going to add on to NH3, and we're going to form NH4 with that additional plus sign because of the hydrogen positive ion. And if I take a hydrogen away from water, what's left over is one oxygen and one hydrogen, and that is the hydroxide ion. So this is that formation of that hydroxide ion through this reaction, why NH3 is a common base, because it's also producing the hydroxide ion according to the Arrhenius theory. Right? So there's a term that we supply to the products of this type of a reaction, and it's called a conjugate. Okay? So we're going to connect the two nitrogen compounds, and we're going to say that this ammonia, which was a base, now on the product side, we're going to refer to as a conjugate acid. And then the two oxygen-containing compounds, if we link those together, water started as an acid. We're now going to call this a conjugate base, which makes sense because a hydroxide ion was one of our fundamental theories of what makes something a base. Right? So if we were to flip this and put these on the reactant side, this now is going to act as an acid and push that hydrogen back onto the base, reforming the NH3 and the H2O. Okay, so in acid-base chemistry, we're also going to be taking some time to figure out what's actually exchanging in the chemical reaction. Now, going along with the theories of acids and bases, we're going to be talking about some of the properties of acids and bases. So some examples is a nice visual that I pulled off the internet. A lot of fruits have a lot of concentrated like citric acid and things like that, pineapples, limes, lemons, apples, kiwis. So things that give a really tart, sour flavor are tart and sour because of their acidity. Okay, so some of the properties over here of things that are known acidic. All right, they have a high concentration of hydrogen ion. And so this term, remember, concentration is really referring to the molarity. And there's a simple abbreviation that we're going to write. Instead of writing the word molarity or the word concentration all the time, anytime we're referring to the molarity of a particular substance, we're going to put that in brackets. So H plus in brackets is referring to the molarity of the hydrogen ions. So that number of hydrogen ion moles per liter for anything that is acidic is relatively high, and the concentration or molarity of our hydroxide ions is relatively low. And this again is what makes certain foods taste really sour. So the identification of a substance based on its sour taste could indicate that it's highly acidic. On the contrary, bases are kind of counterpart or in opposition to acids. So bases have low concentrations of hydrogen ions and high concentrations of hydroxide ions. They taste particularly bitter and they feel slippery. It's kind of an interesting byproduct of anytime something that is highly basic or has a high concentration of hydroxide ions, when it comes into contact with the skin, the oils and the fats in your cells react with the hydroxides faster than they do with the hydrogen ions. And one of the byproducts is turning your oils in your skin into soap, which is why anytime you work with concentrated hydroxides, if you get it on your skin, it really feels slippery, like you just got soap all over your hands. So a lot of common bases are household ingredients like baking soda, lye, which is like an old kind of dishwashing ingredient, ammonia,